In this video, we are going to examine the consequences of viscous boundary layers in rotating flows. We will look at how viscosity near a boundary breaks the geostrophic balance, and then derive a mathematical description for the flow within this viscous boundary layer, known as the Ekman layer. Start by considering a teacup of water rotating at omega. The water is moving exactly with the cup, a state referred to as solid body rotation, so that in our inertial frame the velocity u is simply a function of radius omega r. In the cup's reference frame, the water is at rest. Being at rest means that there is a balance of forces on the water. That is, the centripetal acceleration experienced by the water as omega cross r, or omega squared times the radius, is balanced by the radial pressure gradient within the water, 1 on rho dp by dr. This equation can be integrated in the radial direction from a radius of 0 to r, giving the pressure difference between 0 and r as half density times omega squared and the radius squared. Consider the water to be hydrostatic, so the pressure at Rz is just the density times gravity times the difference between the free surface height at R and Z. This is substituted into the pressure integral to return the difference in height between radius of 0 and r as omega squared times r squared on 2 times gravity. That is, the free surface is parabolic in r. So, for solid body rotation, the radially outward centripetal acceleration must be balanced by a radially inward pressure gradient, which is achieved by the free surface adopting a parabolic shape. Now, in this balanced state of solid body rotation, slightly slow the cup to omega s, so that the water is now spinning faster than the cup. In our inertial frame, the water remains at u equals omega r, while in the cup's frame, the water velocity is now delta omega r. The centripetal acceleration in the interior remains balanced by the radial pressure gradient. However, at the base, next to the boundary, the water velocity has slowed to u equals omega sr, reducing the outward centripetal acceleration to omega s squared r. This no longer balances the inward radial pressure gradient, so the water in this boundary layer flows inwards. Over time, all of the water in the interior will flush through this boundary layer and slow to the new solid body rotation of omega s. This is referred to as spin down. Continuity requires this boundary layer flow to go somewhere once it reaches the center. Here you can see it forms a central cyclone. If we consider the opposite perturbation, that the cup of water at solid body rotation omega is accelerated to omega f, then the centripetal and pressure forces in the interior are still balanced, but at the base the water is accelerated to omega f r, increasing the outward centripetal force to omega f squared r. This is now larger than the radial pressure gradient at the base, so water in the boundary layer flows outward. Again, this continues until all of the fluid in the interior is flushed through this bottom boundary layer, where it is accelerated to the new cup rotation rate omega f. This is referred to as spin-up. These simple conceptual models describe the motion in 2 dimensions only. In reality, while the concepts remain, it can be a bit more complicated, as we are about to discover. Picture a uniform geostrophic flow of velocity big U0 in the x direction. It is geostrophic, so the Coriolis force 2 omega big U is balanced by the pressure gradient in the y, the across flow direction. The equations describing the force balances are 2 omega big U equals -1 on rho dp dy, and given that the flow in the y direction is 0, geostrophy requires that the pressure gradient in the x direction is also 0. Near to the boundary, viscous stresses penetrate some vertical distance delta into the fluid, reducing the velocity in this viscous boundary layer and thus reducing the Coriolis force here, rendering this force unable to balance the across flow pressure gradient, initiating a flow in the y direction. That is, near to the boundary, the flow begins to rotate with height. We are now going to go through the derivation of equations to describe the flow within this Ekman boundary layer. We begin with the viscous, steady, rotating momentum equations. These are the geostrophic equations in x and y with their respective viscous terms, and the hydrostatic equation in the vertical. We want to solve these equations given the boundary conditions of u equals v equals 0 at z equals 0 at the boundary, and that u goes to big U naught and v goes to 0 as z gets large. Now, the hydrostatic equation implies that the interior pressure gradient also applies in the boundary layer, allowing us to relate the interior geostrophic balance equations to the boundary layer equations. This removes the pressure gradient in the x direction, giving 2 omega v as equal to the x viscosity term. It also allows us to substitute 2 omega big U naught for the pressure gradient in the y direction, giving 2 omega times the difference between the velocity in the interior and in the boundary layer as equal to the y viscosity term. These two equations are second order, and considering our limited boundary conditions, we will need to take them to fourth order to solve for u or v. We can avoid this by introducing the complex variable I. Note that this is just a mathematical tool, and that the flow associated with the complex variable is not actually imaginary. If the flow is indeed able to be modelled by these equations, we should be able to perform whatever mathematical tricks we like to examine the flow in different ways. So we multiply the second equation by I and combine. These reduces to give 2I omega outside of u plus IV minus big U naught minus the viscosity times the second vertical gradient of u plus IV is equal to 0. Next, we define big Z equals to u plus IV on big U naught and substitute this big Z back into the combined equation, giving viscosity times the second vertical gradient of big Z minus 2I omega outside of big Z minus 1 equals 0. This is now a second order equation in big Z. We want to solve for big Z with the boundary conditions of u and v at little z equals 0 and little z goes to infinity. The solution is z equals 1 minus the exponential of the square root of 2I omega on viscosity times little z. This solution has real and imaginary parts, which can be separated and rearranged for u and v, where we have made the substitution for delta as the square root of viscosity on omega. These equations describe the flow within the Ekman boundary layer, which has a thickness scale of delta. The flow described by these equations is referred to as the Ekman spiral, the result of viscosity in a geostrophic flow. We can plot these solutions to get an idea of the shape of the flow within the Ekman layer. Velocity in the long flow goes from 0 up to big U naught. Velocity in the across flow goes from 0 to some maximum at an intermediate depth just under 1 delta before dropping back to 0. Plotting these two together gives this distinctive spiral, the Ekman spiral, as you traverse from the boundary vertically through the Ekman layer. Note that immediately adjacent to the boundary, the flow is at 45 degrees to the interior flow, and that integrating the velocities through the boundary layer will give a transport that is normal to the free stream direction. As an exercise, estimate the thickness of the Ekman boundary layer for a laboratory experiment with water and rotating at 1 radians per second, and an atmosphere and ocean with eddy viscosities of 1 and 0.01 meters squared per second respectively. How do these values agree with your intuition?